This video is made for the course in ENSC111 Thermodynamics for this first semester of the academic year 23 to 24. Although our class is already face-to-face, I still decided to make a video recordings for this, for the topics that we'll be discussing or have discussed already, so that at least for those students who wants to have a review, they can have something that they can use. And also for situations wherein there's suspension of classes or shifting of classes to online class, or maybe asynchronous classes, then at least having this complete playlist or recordings, at least we can still progress in our course. Okay, so for the topic number one, we have the fundamental concepts that we have already discussed in the classroom. But again, since we're trying to make a recordings for this, then I have to run through it again. So for the contents of this first topic, we have here first is the introduction. So we will have an overview of what thermodynamics is all about and how it emerges into a science. And then next is we have here thermodynamic analysis and the thermodynamic systems and properties. So basically, thermodynamics is the science of energy, and that means we want to analyze, or actually later on, where we are going to analyze a lot of systems about the energy and the transformation of energies. So we need to have the solid foundation first about the tools, or let's say the principles or the notations that's used for this analysis. And then next we have the thermodynamic properties. Although at this point we're just going to have an overview of the many thermodynamic properties, we're not going to delve into the details of each properties because that's going to be tackled in the next topic. Next week topic, the topic number 2. Then next, for number 5, we will introduce the term state, process, cycle, and also the thermodynamic equilibrium, and also the other laws of thermodynamics. And lastly, we will review some units and measurements. So to start, thermodynamics is derived from the Greek words thermi, which means heat, and then dynamis, which means power. So basically, we can say that thermodynamics is the study of the power of heat, or the heat's ability to generate motion. It actually birthed out as a science during the Industrial Revolution, where steam becomes a power source for a lot of machinery, like here, for example, for transportation, locomotives. It's actually the steam doing this motion. So that is why we said earlier that it's the study of the power of heat, or the heat's ability to generate motion. And the the heart of this machinery, or the industrial revolution, is actually the steam engines. So right here we have a schematic of a steam engine. We have here two containers. So one is filled with water and it's being heated up. So basically this is a boiler, right? This one is a boiler, and the other one is a piston and a cylinder. So this piston is a mechanism, I think, that translates the or that converts the translational motion, or the linear motion. We have here linear motion because piston only moves up and down in this cylinder, and it translates or converts this motion into a rotational one. Okay, so if I try to draw this in 3D, here's our piston, and here's our connecting rods, and we have here shaft. Here's our cylinder here. So this one, we have here pins, so that means this can rotate. So it can rotate, and this piston moves up and down. So as it rotates, and somehow there's going to be rotational motion here in the shaft. And whenever we have rotational motion, or shaft motion, then we can actually attach a lot of devices to it, and we can have um, some applications. So, in detail, here's our boiler. So it's a tank filled with water, and because it's being heated up, then that means at some point in time it's going to evaporate. It's going to change phase to steam, and that steam will travel in this or along this pipe and then transfer to this cylinder, and that steam is going to push this piston. So it has a power to push that piston. Okay, so the interest during the time is how much heat can I input here and be converted into this motion power here. Right, so if we just write, okay, what's going to be the heat here, or how much heat can we input to that system, and how much energy or work that we can get from it. Okay, so actually it's the development of thermodynamics actually spans for years. It's not just one time, but rather there's a lot of debates regarding the developments or the theories. But finally, it came or uh, it became a science finally. So the power of thermodynamics actually lies in its ability to be used to analyze a wide range of energy systems. So although we started with this with the steam engine, actually it merged out to be able to solve actually a wide range of energy systems. So it uses here says using only few tenets or two primary ones, being the first law and the second law. So the first law of thermodynamics is basically about the energy, and the second law is all about the entropy. So when I say energy, it's something that in elementary definition, it is defined as the capacity to work, or you can say something that can produce an effect or has the capability to produce an effect. So it's not just work actually. Okay, and the first states that energy is conserved. So that means that, let's say, here's our system, here's our engine, for example. So if I put in heat here, let's say 100 kilojoules of heat or input energy, then what's gonna be my output? So when I say energy is conserved, that means that the maximum theoretical value of or magnitude of energy that I can get would be 100 kilojoules. So I cannot get 120 or greater than 100 kilojoules, because the first law says that energy is conserved. The statement here is actually they say that energy is neither created nor destroyed, but it only transformed to one form to another. So the maximum that we can get is 100 kilojoules. But the second law, states that entropy is generated. By the way, this is just a basic statement, because there's actually a lot of statement for the second law, a lot of ramifications for the second law. But at this point, maybe we can appreciate what entropy is if we just say that entropy is generated. And when we say entropy, we can say that it's the dissipation of energy. Dissipation of energy. So that means that the final output or the useful output that I want is not going to be 100 anymore. So again, if I input 100 kilojoules, that means that the output here that I want is not 100 anymore. It's going to be, let's say 20 kilojoules, and that means in order for the first law to be true, then that means some of the energy will go into waste, or something that we cannot use it anymore for our intended work or intended output. So that means the 80 kilojoules of energy is lost into the surroundings. Okay, so that means we can only use less than 100 kilojoules because there is this dissipation of energy. So some of the energy we can actually utilize for our intended output. Okay, so again, the first law is about the conservation of energy, and then the second law is all about the generation of entropy. And when I say again entropy, that means the dissipation of energy. Take note, it says dissipation, so that is actually dissipation in the sense that it's not actually dissipated because um, it says here energy is conserved, so that means the total 80 plus 20 is still going to be 100. So when I say dissipation, it's dissipation with respect to our intended output. So we want this output, for example. So let's say going back to our engine, let's say here's our piston right here, and here's our cylinder, and another here the boiler. So let's say we input energy here of 100 kilojoules. So that means the output here, the work output that we can get, is just 20 kilojoules, or I mean just an example. So that means some of the energy is actually lost into the surrounding, and if we account that, probably it's going to be 80 kilojoules, or the sum of this will be the input. Okay, so this is dissipated energy. Okay, so that's the concept of the two principles. So now it says here, since every system is associated with an energy and an entropy, and thermodynamics now apply to a large array of energy systems. So it's not just the steam engines, but actually a lot of systems, a lot of engineering devices, because it involves energy and transformation of energies. So we can say that thermodynamics is now the science of energy, and its transformation, and of course the laws and principles governing the transformation. Laws and principles governing the transformation. So for example, we have here an electric motor. So electric motor, from electrical energy, our output is mechanical energy. I mean energy in a form of rotating shaft. And then here we have a lamp. So we have, if we plug this into the convenience outlet, then that means we get, or the input is electrical, or electricity, or energy in terms of electricity. Then we have an output of light, so energy in the form of light. And then we also have here the internal combustion engines, and there's also energy transformation here, and also or it can be applied as well to a power plant, for example, or manufacturing plants or buildings. We can apply thermodynamics as well, and even in biological systems. So it's all about the energy and its transformations. Okay, so next one is the thermodynamic analysis. So since we are interested in analyzing the system, or let's say the devices, in terms of the energies and the transformation of energies, then we need to have some methods or idealizations on how to do the analysis. So here we have three terms: the system, then the boundaries, and the interactions. When you say system, it's basically anything that you want to analyze. And then the boundaries is going to be the extent or the scope of your analysis. And then the interactions are the energies, or the mode of energy transfers that goes into that system or out from the system. So here are example. So let's say we have here a vehicle. So in this vehicle, we can have this entire vehicle as the system. So that means if we want to analyze the vehicle only, then here's going to be our boundaries. So we use a dashed line to to say that that's going to be the boundary or the extent of our analysis. We only want to analyze the entire vehicle. And then we can have also, let's say we can choose, let's say we just want to analyze the engine right here only. So if we want to analyze the engine only, then we just select this engine and then draw this dashed line, so that that's going to be the scope of our study, or the system. Or we can have, since internal combustion engines, there's actually pistons here. Let's say we have 4-cylinder engines, we have 4 pistons, and we just want to analyze only one part, and it's not just the part, or not just the piston, but rather, let's say we just want to analyze this gas or the substance inside this, or the fuel and air mixture. So that can be a system. So that is why when I say thermodynamic system, is basically anything you want to analyze. It could be the entire vehicle, or it can be the engine only, or other components in the vehicle, or this this portion right here inside this internal combustion, or the combustion cylinder. So that's the thermodynamic systems. And the boundary is the extent of the analysis. That means that let's say if we want to study only the engine and the energy that's crossing these internal combustion engines, that means that external to the engine would be the surroundings. So we call it surroundings, that is external to the system concerned for a particular analysis. That means the other parts here, other components like the radiators, the fans, other components, the tanks here, or that transmission may be here. So it's going to be external, or it's going to be a surrounding with respect to this internal combustion engine. Okay, so that means if this is our system right here for the gas only, that means the piston is going to be a surrounding, and then the valves here is going to be the surroundings, or the components here, or the injectors or other components. That's going to be a surrounding with respect to the system concerned here. Okay, and then for the interactions, we say that interactions are the energies crossing the boundaries. It can go into the system, or it can go out from the system. And actually, it's the mode of transfer. It refers to the mode of transfer of energy. So take note, it's not the energy itself, rather it's the mode of energy transfer. So in terms of modes, we can transfer energy into or out from the system by heat, or by work, or by mass. So in terms of heat, it's a mode of transfer of energy by virtue of temperature difference. Like for example, here in our figure, let's say we have a flame, and we have here a container, and we have a liquid, let's say liquid water. So because we have a higher temperature here, so T high, and right here is going to be lower temperature, there's going to be a transfer of energy by virtue of temperature difference, and we call that mode of transfer as the heat. And sometimes actually they just say heat is energy, although it can be said that way, but maybe in terms of precision, maybe it's not going to be precise. So it should be a mode of transfer. And then in terms of work, then work is another transfer of energy that is not by temperature difference, and it's also not going to be in terms of mass. So since it encompasses actually a lot of possibilities on how to transfer, that's not just by temperature difference, then we'll just say that work is anything that is not caused by temperature difference. Or we say that if it is not heat, then most likely it is work, if of course if it is not through the mass of the system. So again, if it's not heat, then most likely it's going to be work. So for example, here we have a container, and then we still have this liquid substance or water, and we steer this container or this substance. So if, since we induce mechanical action, that means it's going to be work. So we introduce energy into this substance by mechanical work. So it's not by temperature difference. Okay, and then in terms of mass is also transferred. Sorry, energy is also transferred in terms of mass, because the mass that goes into the system, it carries energy as well. So therefore, when it enters the system, then it adds energy to the system, and if it leaves the system, then it extracts energy from the system. So they are just mode of transfer of energy. Right here we have other examples of work, because there's actually a lot of work transfer. So modes of work transfers, but I only have here 3 examples. So 1, 2, and 3. So one is rotating shaft. So this is a work transfer. Whenever we have this shaft, it's rotating, then it's obviously a work transfer mode. Okay, another one is this electrical supply. So electrical supply is also considered as a work transfer mode, although it's not the basic description of the work from mechanics, that work is equal to force times distance. So since there's no distance involved here, unless we are referring to electrons or the charges that moves, then maybe that can be defined that way. But since this is non-mechanical, then and also this is not by virtue of temperature difference, so therefore this is going to be electrical work. And this one is let's just say shaft work. Then for number 3 is, if here's our substance here, let's say it is a steam or a gas, then it has this capability to push this boundary here, right? So let's say the boundary is the piston, so it has this ability to push that, and that is actually a work, and we call this work as the moving boundary work. Okay, so that's I think that's the common work transfer modes that we will encounter later on, although there are still some more other work transfer modes. For the sample problem number 1, we have here, consider a kettle with water being heated up on a stove. Sketch the following system, its boundaries, and the interactions. So here's our kettle, and it has this water, and it's being heated up by this stove. And of course, the stove would be having this fuel tank or LPG tank right here. So let's say here's our entire system, and the problem says that, let's say for letter A, we only need to consider the liquid water in the kettle only. So if we want to study the liquid water only, that means our system would be, or we need to select first the boundary. So here it is. Then what's going to be the interaction? So take note, it says only heating it from 30 degrees to 70 degrees C. So that means we're not changing the phase, or we're not converting the liquid water into steam. Then what's going to be the interactions? So that means we still have this mass of water inside. That's our system. So we have here the heat. Right, so heat transfer. This is Q. So heat is input into the system, or goes into the system. So that's for letter A. And then if for letter B, the entire kettle and the liquid water in it. So that means we need to consider all this. So here's our system. And then assume that it reaches boiling point, so that some liquid water is converted into steam. Okay, so again, we still have this heat input. And then we have here some steam that goes out. So let's say mass of steam. Right. So that's the answer for that. The next is the burner plus kettle. So in this case, if we want to analyze both the burner and the kettle and the water inside, that means we need to what's going to be the interaction. So first is we have this gas here going into the burner. So we have this mass of fuel, and then again, let's assume it reached its boiling point, and therefore some of the steam also went out. So M of the steam, and also since let's say we'll consider, so assume or consider heat losses. So that means some of the heat are lost to the surroundings. Okay, so I think that's just the interactions. And then for letter D, the LPG plus the burner. Okay, so in this case, LPG plus the burner. So I'm going to sketch this. So assuming it's already switched on, so burner is already switched, burner is turned on already. So that means our interaction would be the heat output. Okay, so no mass that's entering this LPG tank, because all the mass that exits here are being burned. So maybe we can say exit or mass of the exhaust or burned gases. Let's just say burned gases, so we can have that. Okay, so that's for our sample problem number 1. Okay, the next one is for problem 2. Consider the compressor tank assembly as shown. Sketch the thermodynamic system boundaries interactions for the following situations. So here's our assembly. We have here a compressor. A compressor is a device that that moves air, of course, at from lower pressure to higher pressure. So it sucks air inside this compressor, and then it outputs the compressed air. So when I say compressed air, that means higher pressure. But in order for this compressor to work, there must be some electric motor. Okay, so that is why we have here electric motor, and this electric motor is connected to some wall outlet. That the compressed air is being stored inside the tank. Okay, so this is a closed tank and this is a rigid tank. So for letter A, if we consider the entire assembly, that means our boundary will be this one, and the interaction would be we have an air input, and then we have a work input also. So we have work here and mass of air input. Again, for letter B, if it's going to be the compressor only, then it means, let's say here's the compressor. Then we need work from this electric motor, so work input, and then we also have mass in from the air and then mass out. Okay, I think that's it. And then for letter C, compressor plus electric motor. So if this is the case, let's say here's the compressor, then here's the electric motor. terms of interaction, we have here the work, electrical work, and then we have the mass and mass of air, and also what else, the mass of air that's exiting the compressor. Then for letter D, electric motor only and include heat loss. So let's say here's our electric motor. So we have work output, shaft work, we have also electrical work, and we have heat losses. And let's say we want to consider the tank only. So if it's just the tank, that means we only have mass here, mass input. So there's no other energy interactions. We are just simply filling the tank. Okay, so I think that's all. Then